Welcome you all in this talk on compact spaces. As you have seen in the course of reanalysis that a closed and bounded subset of Rn or a closed and bounded subset of R is called a compact set. Now the question is whether this definition is also holds good in the setting of metric spaces. Second is why do we need the concept of a compact set? Here is you might be heard that every continuous function defined on a closed bounded interval has a maximum and minimum. Every real valued continuous function defined on a closed and bounded interval has a maximum and minimum. In other words, every continuous function defined on a compact subset of Rn has a maximum and a minimum. So, instead of considering closed and bounded set, can we say that it is compact in the setting of metric space? So here it is well known that every sequence in a closed and bounded subset of R has a subsequence converges in it. This result is not true in general metric spaces. The metric spaces in which every sequence has a convergent subsequence are called sequentially compact. So, what is the difference between sequentially compact and compact? So, we will see these things in this talk. We present the definition of a compact set or the compact space in a metric space and its characterization. We will discuss the Bolzano-Weierstrass property in the setting of a metric space. We also prove that the Bolzano-Weierstrass property, the definition, the compactness and the sequential compactness are equivalent in the setting of a metric space. Now the question is, so first we define the cover of a metric space. So suppose here you have this is your metric space. Okay, let me call this metric space is your X. Now you have the sets. Suppose this is your set, this is your set. Here you have set. This is your set. This is your set. This is your subset of X. This is your subset of X. This is your subset of X. And this is your subset of X. This is your subset of X. And so on, so forth. So in this way, you can see that if we take, let me call this is my G1, this is my G2 and so on and so forth. So if you take the union of all GIs, and GIs are what? GIs are the open, GIs are the subsets of X. So if I let us take lambda is any index set. So if I take the union of GIs and it is equal to X, that is to say the union of, if we have a family of subsets of X whose union is equal to whole space, then this family is called the cover of X. As you have seen in the marriages, there are which we call Shamiana. So on the top of the roof, you have a Shamiana, and the Shamiana is covered, the whole Shamiana is covered by the patches, a different kind of very beautiful patches you can see in the marriages. And that Shamiana, that these patches cover the whole Shamiana. So if you consider the one patch as a set, so and take the union of all these sets, it will cover the whole Shamiana. So these the union of these sets is called the cover of the Shamiana. Or if you have, for example, here a G1, G2, Gn, okay, is any index, any family. It is countable family, finite family, uncountable family, no matter. So, if you have a family of subsets of X such that the union of these sets is equal to whole space, then this family is called cover of X. Okay, so let us take X is your any metric space. So let X be a metric space and lambda be any index set. Then a collection F of subsets of X is called a cover of X if the union of all GIs is equal to whole space. In other words, you can see that if we have, suppose this is my metric space, okay, and here you can see that I can take like this, okay, these are my sets, okay, these are my sets, and this is my set, okay, this is your my suppose G1, this is my G2, this is my G3 and G4 and so on and so forth. And then you can see that the union of GIs is equal to the whole space. It means that if you take any point of the set X, then there must exist, this point must lie in at least, it may be something like this, another set, and here you have another set. So this must lie at least in one member of this family of F. So F is your family of G alpha, alpha is in lambda. Then this family G alpha is called an open, this is called a cover of X. Okay. So now X is a metric space, lambda is an index set, and F is a family of subsets of X. Then this family of subsets of X is called cover of X if the union of all these subsets is equal to your whole space. Okay, if the element of this set, okay, if the element of this set are open set, then this F is called an open cover of X. If the element of this family are finite, this F consists finite number of sets such that the union of all these sets is equal to X, then this family is called a finite cover of X. And if you have a subfamily, for example, let us take again, here you have, this is my space, okay, so I take this one and this one, these are my sets, okay, these are my, okay, so these are my sets, and now I take this one, this one, this one, or you can take other one, okay, so I have patches here, okay, to make it nice, okay. So suppose this is my G1, this is my G2, this is G3, and this is G4, okay, this is G5, and this is G6, this is G6, and so on and so forth. And then you can see that if you take the union of this, then it is equal to the whole space. But the same times, if I take only G2, okay, and this is suppose is this is your G6, this one is G6, this is your G7, this is your G8, this is your G9, this one is G10, this one is your G11, this one is your G12, and this is your G13. And then you can see that with G13 only G1 union G13 is equal to whole space. And so this if I write O is equal to the G1, G2 and G13, then the O contains only 13 numbers, that is a finite number of element. There are finite number of elements in O, but the union of this all Gi is equal to whole X. So, but this is what? This is a subfamily of the family F, where you consider G1, G2, G3 and all these families. So, this family is this subfamily of F is called subcover of X. So, a collection C of a cover F, a subcollection C of a cover F of X is called a subcover if C is itself a cover of X.